Department of Rubber Technology and Polymer Science, Prince of Songkla University, Pattani campus. Today I'm going to be presenting my research work, my research focus, basically on the correlation between mechanical strength and crystallization of natural rubber filled with halloysite nanotubes. Before I'm going to be presenting my research work. My presentation will be covered on the brief introductions and followed by objectives of the study, experimental setup, and followed by results and discussion. And finally, I will end up with a conclusive remark. Okay, as we all know that natural rubbers, here is the para-rubber tree, right? So it can give so many raw materials. As for example, like sap, natural rubber latex, and then or rubber sheet or rubber in bale form. Or even in rubber wood, we can take the from the rubber tree to become a rubber wood and to make a furniture afterwards. And even though the rubber seed, we can also extract the rubber oil seed and to make other products as well. Focusing on this one, we are focusing on the natural rubber itself. Natural rubber itself, this is the chemical structures of natural rubbers. So natural rubbers consist of very unique properties. For example, like strain-induced crystallization. Such induced crystallization can give remarkable properties to the natural rubbers. Even the cis isomer from natural rubbers itself, it can give various advantages. Talking about natural rubbers, comparing with the synthetic rubbers, natural rubbers can give like a strain-induced crystallization. At lower strain or lower deformation, nothing happen. It's just like SBR or synthetic rubbers. Once we apply a high stretching or higher deformation, it can give the stress will upturn is sharply increased, meaning that there is a strain-induced crystallization occurred in the natural rubbers. We can observe the strain-induced crystallization by seeing through the stress strain curve. As we can see here, the stress strain curve, and we can see. And another methods to check the strain-induced crystallization, we can also study through the XRD or X-ray diffractions. As we can see here is the two different patterns of natural rubbers. First one, the red line is the normal state or unstretched compound, unstretched rubbers. Nothing happened to here. That means only amorphous regions over here. Once we give a strain or stretching, it can give two distinct crystal peaks over here. That means there is the crystallization occurred in the natural rubbers. But this case is only happened after being stretched at certain strain, at higher deformation. Okay. Even though natural rubbers can give a remarkable physical properties, the idea to include the fillers is still been focused. There are so many types of fillers nowadays, and they have its own geometries. For example, like cubics or particulate or rod or needle-like or whatsoever. So here's the example of the commercial fillers or the fillers that have been used in the current research. For example, like silica, nanocellulose, CNT, spheolite, carbon black, graphene, and even organoclay. Organoclay is now been interesting fillers that have been used in many polymer metrics. Now I'm focusing on the clay, on the clay. So in my case, I'm studying the incorporation of halloysite nanotubes. Halloysite nanotubes is basically or chemically similar to clay. It's similar to clay, but the different thing is the geometry or the shapes is different. Clay is normally stacked together and laminates together. And then, but in case of hollow site nanotubes, it's different. It's coming from the layer and fold and making like hollow tubes. And then the inner is just like this. And fold together into a tubes. The inner surface of clay consists of hydroxyl groups, and on the edge also a hydroxyl group, but the outer surface consisting of the siloxane groups. It's just like the normal mineral fillers or clay or silica or whatsoever. In this study, I'm focusing on the use of hollow site nanotubes in natural rubbers and see what will happen to the strain-induced crystallization afterwards. It can, we have observed that the hollow site nanotubes can enhance the strain-induced crystallization of natural rubbers. Okay, before going to my experiment, let me briefly introduce some major factors affecting the reinforcement. Reinforcement means once you put the fillers inside the natural rubbers or polymermetric or whatsoever or other polymermetrics, it can improve the mechanical strength or mechanical properties. So there are some major factors that affecting this kind of properties. For example, like filler dispersions or volume fractions. So once we increase the volume fractions, the fillers will agglomerate or aggregate, so making the properties drops drastically or whatever. Then there is a certain amount of fillers and certain dispersibility that can give optimum properties to the rubber composites. And other than that, aspect ratio, filler aspect ratio, and then filler shape or geometry, as I mentioned before, can also affect the properties of the rubber composite or polymer composites. Here we can see the fiber needle-like fillers. As far as the surface areas are increased or a large surface area, it can give a more contact area. Once there are more surface area, that means contact area is improved. So making the rubbers or polymer matrix mechanical properties being enhanced by this kind of appearance. So this is the example of the bound rubber content. Once we increase once we reduce the size of fillers that been used in the rubber or polymer matrix, it can increase the bound rubber content. So here is the example. We prefer as small as possible and high aspect ratio as possible to make the polymer matrix become more strength or whatsoever. And last but not least is the compatibility. Compatibility between fillers and polymer matrix. As you can see here, different fillers, each type of fillers has their own surface chemistry. So we have to look back whether the surface chemistry of the fillers or the rubbers is compatible together or not. Then we can observe later whether the properties is enhanced or whatsoever. Here is the example of the surface chemistry on the fillers. For example, like HNT, in my case, carbon black, silica, and so on. Okay. Once the reinforcement is there, so normally we have to check. We have to investigate whether there are the reasons behind the reinforcement or not. So normally we check the bound rubber contents. The more rubber content, the bound rubber contents, that mean that there is the rubber filler interactions. So we normally we normally study the rubber filler interactions in order to support the research findings. And another thing is pain effects. Normally, this kind of study, we study over the strain amplitude, the strain rate. Once we input high strain, then we see whether the filler network is there or not. If the rubber filler interaction is there, so the differences between storage modulus at lower strain and higher strains will be reduced. The the small differences, that mean there's high rubber filler interactions. And other methods, there are the detailed investigation on this kind of works as well. For example, like FTIR, to observe whether there are some functionalities, appearance, or disappearance. Then from this, we can make a correlation between our systems. XPS studies, we also observe the XPS studies to see the binding energies between two connecting atoms, depending on the atoms observed on the each and every type of fillers. And RS mean Raman spectroscopies. We also use the Raman spectroscopies to see any bondings, the additional bonding in there or not. So there are so many works also use the Raman spectroscopy to support the findings. In my case, I'm interested in studying using XRD because my fillers is a kind of crystalline fillers. So basically, I chose this kind of technique to confirm my research findings. So in case of organoclay, they use this kind of technique to confirm whether there is the intercalation between two different stack of layers. So if there is a peak shifting into a small angles, meaning that there is intercalations of the rubber inside the clay laminations. Okay. In my work, I'm focusing on the use of, we call it a wide angle X-ray scattering. We call it wide angle X-ray scattering. It's compared to, it's like a typical XRD. The thing is, the sample is here, and then once the X-ray source, the object to the samples, it will scatter into different angles. So actually, there are two types of X-ray scattering. There is small angular scattering and wide angle scattering. So small angle scattering, there is no vacuum tubes over here. But in case of small angle scattering is equipped with a vacuum tube in order to reduce the scattering angles. Depends on the materials or what are you going to study, whether you are going to choose the wide angle or small angles. So in my case, I have studied using typical XRD first to see whether my interested peaks are in the range of wide angle or not. Then we choose whether to choose the wide angle or small angle scattering. Okay. This is the previous image that I've shown you before. If there is a strain-induced crystallization, there will be, there are two peaks, additional two peaks appear. This is kind of amorphous. This is kind of crystalline region of appear after being stretched. Okay, this is the it's kind of 2D image from the wide angle techniques. Because I study strain-induced crystallization, so the sample should be stretched, and then we monitor the crystal peaks simultaneously. So normally the extension apparatus or extension equipment is here. Then we keep on stretching, and then monitor, detect every single strain that we apply to the samples and see what will happen to the XRD pattern. Okay, my objective of the study is to study the effects of the loadings, HNT loadings, on the properties, and then make a relationship between the mechanical properties or tensile properties with the crystallizations that observed after being stretched. Here's the formulations and preparation. The composite was prepared in the internal mixers with certain temperatures, certain rotor speed, and the loading were 0 to 10 pSr. as for the testing analysis, we study the curing characteristics and tensile properties. And the next one, the wide-angle X-ray scattering. So we study the degree of crystallinity and orientation parameters to see the orientation, whether it is an isotropic or isotropic alignment. Here's the result of the curing characteristics. This is very common for the kind of clay materials because it's consisting of the siloxane on the surface. So it's basically, it will absorb the accelerators, so making the radicalizing process delay. So this is very common. And even though the maximum torque and torque differences is also a kind of typical findings because we input or include the solid or rigid fillers inside the rubber matrix, so making the rubbers or maximum torques increase or torque difference also increase. This is very typical result, is common. Okay, this is the typical XRD, this common XRD without being applied with a wide angle X-ray or small angle X-ray. So here we can see this is the interested peak of the HNT, which is at the 12.13 angles. This is the crystal peak of HNT. This is just to confirm whether the HNT is there or not. So once we include the HNT inside the rubbers, this is the crystal peak of the natural rubber filled with the HNT. We can see it's like a stoop here. So this is like a amorphous region. If amorphous is there, so it's being like a stoop over here. So nothing is not like linear, the curves, as it is the case of HNT. Oh, here is the stress strain curve. As we can see here at low deformation, nothing happened. But even though the modulus is increased, but with the small changes only, but at high deformation, there is the strain-induced crystallization. So we can see here, once we include more HNTs, the stress, the stress is increased with the addition of HNT. So we can see, but only happen at high deformation. Now, afterwards, I'll make a relationship between the crystallizations characteristics of natural rubber filled with HNT. This is the tensile strength. It's increased with the increasing. This is the result from the wide angle X-ray. Wide angle X-ray. We scan from 2 theta equal to 8 to 20 something, and then we see the strain-induced crystallization. Okay. Yeah, we can see over here. This is being stretched, the sample being stretched. Normally this peak is like a stoop here. Nothing happened to the diffraction peak over here. But after being stretched, as you can see here, the peaks, there is the peak appearance at the plane 200 and plane 120. So this kind of peaks keeps increasing once we input or include the HNT inside the matrix. So as we can see from the 2D image over here, so the more transparent meaning that there is a crystallization occurs in the samples. Yes, once we pick up at the certain we call it angles, we can see here, once we increase the stretching or strain, we can see a distinct peak occurred. That means that there is a crystallization occur after being stretched. This is very common for natural rubbers. But the thing is, over here, the peaks is totally different. Comparing to the normal case without any using of the HNT. This is the 3D image. Okay, we also study the degree of crystallinity, whether there is the more crystallinity as been mentioned before or not. So as we can see here, once we increase, when we increase the amount of HNT, the strain, see over here, the onset is, we can see here at lower strain, the crystallinity of the natural rubber field HNT started to occur. But comparing to the unfilled one, if you can see here, unfilled one and filled one, this figure is very corresponding or very good agreement to the strain, to the stress strain curve. Over here, it's almost the same. So that means we can make a correlations between the tensile properties and the crystallinity or crystallization of the natural rubber filled with the HNT. Here is the schematic illustration or representing the strain-induced crystallizations. So if once the sample was unstretched, so nothing happened to the, as you can see from the 2D image, nothing happened to the 2D image. But once we increase the strain, we can see a clear indication of the crystal image over here. So we can see here. So so it's basically it's like HNT. Without HNT, this kind of things happens at the higher deformation. Once we include the HNT, it's like HNT can rearrange together with the molecular chains. Once it is the strain is applied. So due to the better dispersion and compatibilities between HNT and natural rubbers, it can enhance this kind of effects. So that meaning that HNT can improve more strain-induced crystallization to the natural rubbers. This figures is about the orientation parameters. So basically, it's not so significant, or this result is not quite significant. But as for your ideas, normally if the numbers is towards 1, that means that the orientation is toward anisotropic. That means in the same direction of the stretchings. So once the numbers is below 0 or negative, that means it's opposite. The arrangement is this. We call it perpendicular. That means the opposite the direction of the alignment. But once the number is about 0 or something, that means it's the isotropics, depending on the orientation parameters over here. So we will study further here whether it can make a relationship between our findings or not. So because this result is not so significant yet, but the most interesting things over here is as we can see, once we put the higher amount of fillers at 10 PHR, we can see that the orientation parameters is lower than other additions of HNTs, assuming that the agglomerations is there. Once the agglomeration is there or aggregations is there, so making the alignments, making it change the alignment of the stretching or molecular change. Yes, our conclusive remarks. So as you can see before, the Scotch time and cure time or whatsoever, longer once we include the HNTs or even maximum torque and torque difference is like typical findings because we include the rigid fillers. So that means that we reduce the fraction of the rubber, so making the maximum torque and torque difference increase. Tensile strain and elongation at break we observe at 5 PHR. And then we also make a relationship between the strain-induced crystallization and with and without HNTs. As you can see before, once we include the HNT, making it makes the requirement of the strains at lower requirements, at lower deformations. We use only low deformations in order to start crystallize the natural rubbers composites. So with that, I would like to thank for your attention. Please thumbs up and like on our page. Then you can see all the information is there about our departments.